Okay, so in this video, we'll try to design the same thing that we did the last time, the last video, but this time we'll be using a concept of mealy machine. So in the last video, I gave you the brief difference. In a Moore machine, once you're in a particular state, output is implied. So it would have a fixed output for a particular state. But in the mealy machine, the outputs are, conditional. It will actually depend upon, apart from being in the current state, it will depend upon what the value of the input is. Right? So typically it is difficult to capture the behavior of a problem of a circuit using a mealy machine. But if you are able to capture the behavior as a mealy machine, it generally will require lesser number of states when compared to the Moore machine. So lesser number of state means when you translate that into a circuit implementation, you will have lesser logic. So we have the same problem definition here, the button press synchronizer. Every time you press a button, it will make the output go high for one clock cycle. Then whether you release the button or keep pressing the button, output is going to be zero. So this was a problem discussion. And this was the way we captured it using the Moore machine, wherein we defined three states, A, B, and C. State A, the initial state, where the output is zero. And if you press the button, you will go to state B. If you don't press the button, you will continue to stay in the same state, which means in that case, output will be continue at zero. But once you move to state B, output will be one. You will stay in the state B for exactly one clock cycle. If you continue to press the button, you will move to state C, where it introduces a new state, state C. But if you release, you'll come back to state A. In the state C, the output is zero. If you continue to press the button, you will stay in the same state. If you release the button, you will come back to the state A. Now let's try to capture the same behavior using a mealy machine. I will again have an initial state. Let's call it state A. This is my initial state. Now I cannot specify the output here because this is a mealy machine. Output will be conditional. It will actually depend what my input is. Now in the state A, if I don't press the button, this condition BI complement. If I don't press the button, then my output is going to be zero. And in this case, we show it something like this. We put the condition BI complement is the condition, means we're not pressing the button. Then we put a slash, and after the slash, we put the output. So in state A, if I don't press the button, then my output is going to be zero. Fine. And if I press the button, so let me introduce another state here, state B. If I press the button, then I will move to the state B and my output will be 1. Fine. So this is what I mean by conditional output. Apart from being depending upon a particular state, it will also depend, okay, what is the input in that state. Fine. Now when I reach to state B, again two conditions can happen. I will continue pressing the button, wherein I will stay in the same state and my output will be 0. Fine. Second condition can be I will release the button. Again, my output is going to be 0, but I will come back to state A. And then the cycle will repeat. Right? So if you see carefully, this is a mealy machine where the outputs are conditional. And I have actually reduced one state in the problem by making this small change. The change wherein my outputs are not fixed in a particular state. They actually depend upon what is the condition at the input side. Right? So this is how we capture a mealy machine. So this is the first step. Next other steps, they are the same. So second step will be creating the standard architecture. Now in this case, you have only two states and one bit is sufficient to explicitly code what you call these states. So the standard architecture will change here. It will be, I will only need a 1-bit state register, which essentially is a flip-flop. So this is 1-bit state register. And then I will have the combinational part, which I will resolve in the coming steps. So this is the combinational logic. From the 1-bit state register, I will have a single output, which will act as input to this combinational logic. Again, as a convention, we could call it S0. Then I will have output from the combination logic that defines my next state N0. Fine. And then as usual, I will have an external input BI and an external output B naught. So this will be the standard architecture for the mealy machine. Then the third step is we'll have to encode the states. This is the third step. So like I said, it's a very simple state machine. So for one state, we can use the code 0, let's say for A. For another state, we can use the code 1. Rest of the things, they will stay the same. This is the initial state. If the button is not being pressed, my output will be 0. I will stay in state 0. If the button is pressed first, my output will be 1 and I will move to state 1. In the state 1, if I continue pressing the button, it will be like this. And if I release the button, still my output is going to be 0, but I'll come back to state 0. Fine. Then fourth step is we create the state table, wherein I list the inputs on one side and the outputs on the other side. Now, as far as inputs are concerned, I only have S0 and external input BI. And as far as outputs are concerned, let's say B naught and the next state output N0. Fine. And if I am in state 0, I don't press the button, then my output will be 0, my next state will be 0. If I am in state 0 and I press the button, my output will be 1, conditional. Just a second, let's put it in black. Will be 1, and my next state will be state 1. Then when I am in state 1, if I release the button, my output will be 0, and I will come back to state 0. Again in state 1, if I continue pressing the button, my output will be 0, and I will stay in the same state. From here on, you can easily get the expressions for B naught. B naught is a single term, S naught complement BI, and N naught, it has two terms, S naught complement BI and S naught BI, which is basically BI if you take it common. Fine. So your overall circuit will be pretty simple. You just have a 1-bit state register, which I told you is just a flip-flop. So this is 1-bit state register. This is the clock. You will have one output from here as 0. You will have an external input BI. Fine. As far as your B naught goes, you will have complement this combined using an AND gate. This is your B naught. And as far as your next state goes, you'll actually have a direct connection from here that will be fed back. So this is again a button press synchronizer, but designed using the concept of mealy machine. Fine. So remember, if you're capturing your machine, your behavior as a Moore machine, it means that the state outputs only depend upon the present states. You are in a particular state, output is defined. And in a mealy machine, your output is conditional. Being in a particular state, it will depend upon what the condition at the external input is. So together, the state as well as the external input will determine what your external output is going to be. Like I said, it is slightly difficult to capture mealy machines, but once you capture it, it actually allows you to capture the behavior in lesser number of states, right? Generally speaking. And lesser number of states, when translated into hardware, will result in lesser number of and lesser hardware, right? We'll do some more examples in coming videos about this mover and relay machine. Stop here.